Surface composition of a planet is a vital part of space exploration. But due to engineering and financial limitations, it's usually not possible to send a spacecraft to the surface. In this case, the orbiter must include an instrument capable of remote sensing surface composition from orbit. A neutron spectrometer is one such device. It's a device that counts free neutrons, which are neutrons not part of the nucleus of an atom. When these neutrons move through matter, they're either absorbed, scattered, or simply pass through, unaffected, which is what happens most of the time. They're classified based on your energy level. We're only concerned with three of these levels: thermal, epithermal, and fast neutrons. Free neutrons on the planet are created when cosmic rays interact with the surface up to tens of centimeters deep. When this happens, free neutrons are produced. They start off as fast neutrons, but as they get scattered by the surrounding materials, some will lose enough energy to become epithermal and thermal neutrons. Some may also get captured by the surrounding materials. Eventually, some of these fast epithermal and thermal neutrons will make it to the surface of the planet and escape into space to be detected by our neutron spectrometer. The type and amount of neutrons that's detected per unit time can tell us the following. Fast neutrons are neutrons that didn't interact with any other matter after their initial interaction that created them. They're a good indicator of the density of matter below the surface. They also serve as a reference count for the other types of neutrons. Epithermals are neutrons that have lost some of their energy due to more interaction with matter after their creation. They're a good indicator of certain types of element, including sodium, aluminium, and silicon. Finally, we have thermal neutrons. These are neutrons that have lost most of their energy. This usually only happens when the neutrons interact with hydrogen atoms. The hydrogen atom happens to have almost the same mass as a neutron, so in a collision, momentum is almost perfectly transferred from the neutron, leaving it moving slow, relatively speaking. Because of this, detection of lots of thermal neutrons is a good indicator of hydrogen. Hydrogen, most likely in one of its simplest chemical compound, H2O, or water. This is one way we can determine to some extent the composition of a planet's surface from orbit. So, let's talk about how these devices actually work. As an example, we'll use the Neutron Spectrometer from the Messenger spacecraft during its exploration of Mercury. This device has 3 detectors. Each detector is made of a scintillator and a photomultiplier tube. The scintillator is a special piece of glass or plastic that uses energy from ionizing radiation to create photons, basically flashes of light. The ionizing radiation in our case is free neutrons. The photons created by this interaction is directed to hit the first stage of a photomultiplier tube. This causes electrons to be released. These electrons then hit the next stage of the photomultiplier, which causes more electrons to be released. These go on to hit more stages, releasing even more electrons for every stage. It's like a chain reaction. In the end, you end up with a strong flow of electrons, which is then used to drive the input of an electronic counter. All from a free few neutrons. This is a relatively simple device as far as operational principle goes. But simply detecting and counting free neutrons is not enough to determine their origin and ignore unrelated neutrons emission coming from elsewhere in space. For this reason, the neutron spectrometer on board the Messenger spacecraft has 3 detectors. 2 of these detectors uses a glass scintillator to capture neutrons. They are most sensitive to thermal and epithermal neutrons. The 3rd detector has a plastic scintillator which is more sensitive to fast neutrons. The 2 glass detectors face in opposite direction from each other. The plastic detector is at a 90-degree angle relative to the glass pair. Since these detectors are directional, they can only detect neutrons coming from the direction they're facing. This allows us to discriminate between neutrons coming from the planet and neutrons coming from the immediate surrounding, like dust, or even the spacecraft itself. Remember that the spacecraft is also exposed to the neutron-creating cosmic rays. For simplicity reasons, the Neutron Spectrometer is mounted directly to the spacecraft. This means we cannot change the orientation independent of the spacecraft. So, if we want to point our spectrometer in a specific direction, the entire spacecraft has to be turned. When Messenger began collecting neutron data on its third flyby of Mercury, it performed a special maneuver while doing so. This was necessary to increase sensitivity by pointing the sensor in various directions. Since the sensors are not movable, the spacecraft had to perform the maneuver. The data from all detectors collected during this maneuver is then fed to a signal processor to give useful but still raw data that is then used by scientists on Earth to determine the materials that the neutrons went through on their way from the planet to our spacecraft. This data is good at detecting certain chemical elements, and from that, and based on the ratio of elements detected, we can make a good assumption of the chemical compound that may be present on the surface of the planet. For more accurate result, we would have to land on the surface, but at least we'll know where to land when the time comes. Now for some progress report on my upcoming simulator. The official name is Curiosity 2. This is not related to the Mars 2020 rover. It's simply an update of my 2D Curiosity simulator that's on Google Play. I'm currently working on the turret end of the robotic arm. This is where the drill is located, and that's where my current focus is. Surface contact sensors are now functional. They are there to indicate that the drill is at a proper angle relative to the rock it's going to drill into. They also give the drilling process additional stability during drilling. Drilling can now be performed on a rock, and the depth of the drill can be measured. There's a data model for each rock that describes its composition as a function of depth from the surface. That's the next thing I'll be working on, how to present that data to the user. That's my progress report for this week on Curiosity 2. I'm DexDFX for Sensing the Universe.